Okay, we were talking about the reservoir fluid properties this time, and we talked about the phase behavior in general. We said that like a plan of a house, or we have our phase behavior diagram, something like this one, which represents the reservoir. Every reservoir engineer in his office, he should have these kind of phase behaviors, and every reservoir's phase behavior is different. Every reservoir's disk picture is different, and it tells us exactly at what pressure, what temperature, what is the condition of the reservoir, how much liquid it is and how much gas it is, and at the same time what is the current pressure, what is the current temperature. This is what this phase behavior is about. Then we discussed some types of oil and gas reservoir. For oil reservoir we have low shrinkage oil, high shrinkage oil. Then we have the wet gas, dry gas. We talked about it. We talked about various gas properties, especially the equation of state. We talked a lot about it. We talked about the Z factor. We said that the ideal gas behavior is only at the atmospheric conditions. Real gas behavior at 2000 psi and 100 degrees centigrade is different than the ideal gas behavior. That's why we added the Z factor there. And we discussed that we will talk about the Z factor calculations also. Then the formation volume factor, we discussed a lot about this formation volume factor, expansion factor, compressibility, viscosity. Now I'm going to talk about something very important here, which is the fluid pressure versus depth measurement. Actually, as per I remember, one of my friend had a job, and what his job was is just to be on the software, and data was coming from the well, and he was recording the fluid pressure versus depth, and based on that they were getting whether they have the oil reservoir, gas reservoir, or the water reservoir down. Now let me share with you what's going on here. For example, that our reservoir looks like this one, and here it is. We have reservoir like this one. So what we do during the drilling process, or we run a tool. Sometimes this tool is called the MDT, modular dynamics. This is by the Schlumberger company. They call it MDT. And what they do, this has some logs, the geological logs, which send their waves, gamma ray log or some other logs. They send their waves in the nearby areas. So basically, the software send waves there. This device. Okay, and what they are trying to do, they are trying to know the pressure here in this zone. What is the pressure here in the nearby well? We are not talking about the here or the other corner, just near the wellbore. Just near the wellbore, what is the condition of the pressure? Now this tool, which we call it MDT, is connected with the wire at the surface. Okay, at the surface is connected with the software. Now that software actually generates a chart, which is the depth versus the pressure. Okay, it looks something like this one. Can you see the presentation or the whiteboard?
The whiteboard.
Whiteboard, okay, let me close. something like this pressure versus depth graph is made. Now, pressure, because of their density gradient, the pressure basically is different for the gas, different for the oil, and different for the water. Pressure gradient for the gas has something like this shape. For the oil, it has a shape like this one. From the experience, we know that. And actually, in the software, we just automatically detects it. Okay. So what we do, we based on that MDT tool that I showed you before, we create the profile with pressure. What this tells us that which kind of region we are going through. Are we going through the gas, oil, or the water? Now look at this one. They are connecting this gas, oil, and this one. So between oil and water, there is some transition. So it's showing also the transition stage also. So based on this pressure profile, we obtain our oil water contact, gas water contact, and exactly the depth of the gas, oil, and water. So if I describe it into the words, for example, if we have the gas here, and then we have in the next phase we have oil, and then next the base phase we have water, and it looks like this one. So the graph that at the surface this tool will make, when this tool go through on all these three zones, the graph will look like this one. This is the pressure here, and okay. Now, as you see that we have some lines here, which are quite this line. Then we have another line, which is this line. So based on the pressure profile, we can find out that are we going through the gas zone, oil zone, or water zone. So here is basically the gas zone. This is the gas zone. Then we have second one, oil zone. I'm specifically talking about this zone, starting from there to there. And then third, we have water zone. This one. So the pressure profiles are important, and one of my friends' job exactly just to do this. The software was running inside the hole. He had all the data. He put it in the software. He generated that, for example, the well starting from this point. Let's say depth here is 2,000 meter. Exactly at here point is 2,000 meter, and at this point, maybe it is 2,400 meters. So all his job was just to report that from 2,000 to 2,400 meter is the gas zone. And they had the tools. Of course, he was just an engineer, so he had the software. Software was actually telling him that from 2000 2004, based on this pressure gradients, it was finding out that we are dealing with gas zone, oil zone, or water zone based on the pressure gradient. And he was sitting in office. Basically, there was another engineer who was at the field at the well and who was running this tool inside the home. So, and this operation usually sometimes took like 24 to 36 hours. And they had the chat also going on at the same time. They were online on WhatsApp or they're on their clients. 24 hours, their both side engineers were sitting and they were monitoring the pressures and they were talking to each other and they were trying to identify which zone they are going through right now, gas zone, oil zone, or water zone. So whenever this job, for example, if you are hired as a MDT engineer in Schlumberger, MDT engineer at SLB, so your job will be like this, like you are working 36 hours continuously, then they give you 2 days break. Okay. And when there is no job, I mean, you have to be in office at any time. Doesn't matter, 8 to 4, 9 to 4. Maybe you can go at 6 o'clock in the evening. Maybe you are going at night. So it does not matter. But when the job goes on, uh, the job usually takes 24 to 30, 36 hours, and you have to continuously look at the profile when they are running the tool, because they have to make sure the tool is running straight and there's no obstruction or something like that. So based on this pressure profiles, they find out where is the gas, how much is the depth of the phase zone of the gas, then the oil, and then the water. That's one of the job of the MDT engineer that they do. The same thing is going on here. They have this chart, and especially in the exploration and appraisal well pressure surveys used to determine hydrocarbon contacts and fluid gradients. So they find out the hydrocarbon contact. As you see that the pressure gradient for gas is 0.08 psi per feet, which is lower. For water, density is very high, so 0.45 psi per feet. Oil is in moderate, so 0.35. So lowest is the gas one. Based on these gradients, they find out which kind of reservoir they are dealing with. This is what I said, the gas, oil, and water. This makes a picture here. This red one with the gas, oil, with this green one, and the blue is this one. Sometimes we have different layers. It has different pressures. Pressure plays an important role on volume. Okay. And that's why in all our calculation, pressure plays major role. We have to know layer by layer what kind of pressures we are dealing with. And this one pressure is, see that it's a bit higher than the layer 4 or layer 3. So we have to look for the dynamic profiles when we go for the reservoir management. Like, for example, which reservoir you are going to, which target, from which formation you are going to produce. You can, for example, produce, let's say you can put your well in zone 2. Like this one. You can put the well in zone 2. But at the same time also you can put it in zone 3. Or you can put in all the zones actually. Here in all the zones. So exactly from where you are producing. So this change in the layer pressures, it tells us that what we need to do and so on. Now we talked about the reservoir fluid, we talked about reservoir rock. We have some laboratories for them. Okay, and we do lots of testing in the labs to get those properties that you hear about it. So what properties we want to know in the lab basically? We want to know the bubble point or dew point pressure. We talked about it a lot. Formation volume factor, we talked about it. Gas oil ratio, we talked about it. Viscosity, you know already. Composition from C1 to C10 as we discussed. All these things needs to be obtained from the lab. And what equipments are used to obtain them, I will show you somehow now. And so on. So let's talk about those equipments first.
Wettability and the capillary pressure, like relative permeability, depend on a relationship between the reservoir rock and fluids. Wettability is a measure of the molecular attraction that solids and fluids have when they come in contact with each other. Thus, we say that water wets a glass surface because it spreads out on contact, whereas mercury does not wet the glass because it tends to bead up on that surface. This principle has application to reservoirs. If we look at
reservoir rocks are water wet. This means that a water layer surrounds the rock surfaces, and the hydrocarbons are in the center of the pore. Capillary pressure is the pressure that exists across a fluid interface within a capillary medium. We all remember that if we immerse a capillary tube in water, the water will rise in the tube to a certain height. It rises because water wets the glass. The height of rise depends on the interfacial tension between water and air and the radius of the tube. If the tube radius is reduced, the water will rise higher in the tube. A reservoir rock is a capillary medium. Therefore, the oil-water contact will not be a flat horizontal surface. Water will move up higher in the smaller pores.
Vinci Technologies is proud to present the standard fluid
Sorry, we can't hear you.
Okay, sorry, my mic went off. So what I was saying that uh, this equipment is available in reservoir fluid labs, and the name of this equipment is called the PVT. And the job of PVT is to find out the bubble point pressure, and differential liberation test we do with it. We find out the content of asphaltene from using this equipment, and we do a swelling test. So we do a number of tests using this equipment. Mainly for the bubble point pressure, this equipment is used to find out at what pressure the first drop of gas comes out of it.
Eval. This device is a mercury-free PVT and flow assurance system.
When you go for master, you will definitely see in other.
There are two possible configurations: 500 cc, 20,000 psi, and 200 degrees Celsius; 1,000 cc, 15,000 psi, and 200 degrees Celsius. The PVT system can perform phase behavior studies for black oil.
The phase behavior diagram that I showed you, the data for that one actually comes from this kind of equipment.
Gas condensate samples, and also asphaltene or wax deposition studies. The PVT cell and flow assurance modules are located and maintained in an isothermal air bath. The PVT cell is equipped with a sapphire.
This is actually a chamber, high pressure chamber, where the fluid is inside it under high pressure. For example, 5,000 psi, 100 degrees centigrade. You can put the fluid inside
Window to visualize the gas-liquid interface during the PVT test. A temperature compensated
I have used this equipment.
Pressure sensor with an accuracy of 0.02% full scale is mounted onto the PVT cell. Two dead volume bleed valves are incorporated into the PVT cell to allow sample loading and precise gas takeoff required during differential vaporization and constant volume depletion experiments. A magnetically driven stirrer located in the cell optimizes the phase equilibration process. The speed of the stirrer can be adjusted for the nature of the sample. The PVT system is composed of an embedded pump which monitors the pressure and volume of the sample. The pump piston is equipped with polyamide gas explosion-proof seals. A motorized rocking mechanism enables the end user to set the PVT cell in two possible positions. For PVT oil studies, the cell is in an upright position and the gas is released by the operator using a dedicated bleed valve. For PVT gas condensate studies, invert equipped with a uniform lighting box and a motorized linear stage captures high-resolution pictures of the sample being analyzed under specified pressure and temperature conditions. PVT experiments are recorded in real time and the results can be retrieved after the test for post-treatment. Volumes of retrograde liquid in the cell can be measured at each pressure step. For instance, during a differential liberation test,
for instance, here they find out the bubble point pressure. So this is actually the oil, the brown one you see, it's an oil. So when this bubble comes up here at the top, it tells us
on a black oil sample, the operator can monitor the gas-liquid interface on the screen until total removal of the gas phase. During a constant mass depletion test on a gas condensate sample, the retrograde liquid volume can be measured and recorded. A touchscreen panel is provided on the top of the electric cabinet, allowing the operator to.
For us, this kind of equipments, they were connected with our phones and with our laptop. So we could operate them from the home. Whatever data was coming here, we were looking at from our homes. And this experiment also took 24 hours to 36 hours. So we were following them from home and looking what exactly is the condition. Because if electricity goes off, all equipment is destroyed. All experiment is destroyed. You have to start from zero then. Because we are maintaining the pressure, volume, and temperature inside. And our job is to find the data for the phase behavior that I showed you in the initial slides.
Control the instrument locally. Specifically, the operator can set the cell temperature, start or stop the stirrer, set the position of the PVT cell, and select the operating mode of the embedded pump. A cooling unit can easily be connected to the air bath to provide sub-ambient temperatures of up to -20 degrees Celsius. A remote control.
The cost of this equipment is around 200,000. 200,000. That's why the ordinary universities, a low-budget university, cannot afford this equipment.
Station provides real-time data acquisition, real-time controls, macro commands, video facilities, and PVT report generation. Optionally, a solid detection system can be added to the assembly, permitting the determination of asphaltene onset pressure and wax appearance temperature. An optical fiber generates a near-infrared light through the reservoir fluid, and the resulting transmitted light is utilized to deduce the presence of asphaltene fluid at each state of pressure and temperature. An organic solid filtration system is also available. It is based on two high-pressure, high-temperature filters. The first removes the inorganic particles contained in the oil sample during transfer from the sample cylinder to the PVT cell.
The desired properties out of larger blocks.
Now, earlier equipment was used for the PVT study, reservoir fluid studies. Now, for reservoir rock studies, look at the lab they have there in this TU Delft.
We select and drill cylindrical rock samples or cores with the desired properties out of larger blocks.
This is the rock sample they are taking from the reservoir.
We then seal the outer edges of these core samples to keep the fluids inside and then to allow us to maintain them at the desired pressure and temperature. We mount the cores in a holder and put them into an oven, which then can maintain the desired temperature.
We actually, in labs of master's degree or PhD degree, we often buy these prepared samples like the one they prepared. So usually we don't go for all this process. We just buy the ready sample, that the circular one as you see. We call it a core sample. And this core sample is used to find out the permeability, the porosity, and other properties that we discussed.
We drill into the side of the core holder.
This is the now core holder. They put the sample inside, core sample. They will close it and then they will
Tabs, which allow us to measure pressure. This is important to make sure that we've obtained the conditions we want and also to see how easily the fluids are flowing, how much of a pressure they build up as they flow through the core. We attach flow lines that allow us to inject and produce the fluids, see what is retained inside and what flows out, and how the fluids that flow out have been changed from what flows in.
The cost of this equipment is $150,000. this core flooding equipment. It's a very critical instrument for reservoir study.
Finally, we can actually see what happens inside the core using an X-ray computer tomography machine. What you see here, it's the same technology that's used to image inside the human body in a hospital. Here we use it to see the interactions of fluids inside the rock. We study the flow and interaction of fluids in rock layers by doing experiments with rock samples in the laboratory. So we inject fluids.
So these are the same MRI machine that you use here for human body. They use it for the core sample.
Fluids into these porous rock samples, measure how they interact, how easily they flow, how much they're trapped, and from those experiments predict what happens underground. It's of course much easier to do experiments in the laboratory than it is to do them out in the field.
Look at this picture here, he has posted here. Okay. Where is the bubble point pressure? Well, this is the undersaturated condition when all is oil. And then what you do, you drop the pressure. When you drop the pressure, first bubble of gas come out, which probably is here. And then as you further drop the pressure, the gas forms a separate phase. So here you see that the gas has the separate phases here. But here only single phase, all oil. And here you see it all become, under low pressure, all become the gas. And oil has small pressures.
From these measurements, then we make predictions. For instance, how much carbon dioxide is trapped as it flows through porous rock. This helps us to understand the efficiency of carbon dioxide storage to reduce global warming.
When you go for masters, you will see them there. Those who are interested in masters, they will see this kind of.
It's famously difficult to explain.
This is they are doing the experiment to find the absolute.
Welcome to experiment number 9A, liquid absolute permeability measurement. First, let's understand what's permeability. Permeability of a reservoir is a measure of how much fluid can flow through a rock for a specific pressure drop. Absolute permeability, which is the permeability that we are going to measure today in this lab, is measured of the ability of the single flow, such as water, gas, or oil, to flow through a rock formation. When the formation is totally filled, saturated with that single flow. In petroleum engineering, Darcy's flow equation is used to measure the permeability. This equation is valid for laminar, steady state, linear flow in a homogeneous horizontal reservoir. Therefore, the experiment in this lab must meet those requirements. In this experiment, permeability of a liquid, water in this case, will be determined by using core flooding model. The core sample that we are going to put here is 2.5 diameter, and the length of the core is 2.5 inches diameter, and the length of the core will be 7 inches length. And the porosity of our sample is 15%.
Doctor, we cannot hear anything.
Yes, sorry. I said that this equipment here is called the core holder, and the rock sample that we have actually is inside this core holder. And after we put the rock sample inside this place, this chamber, we close it and we allow the pressure to build up inside it. We have a pressure equipment. We allow the pump to put the pressure here, and then we inject the fluid using those pipelines. There are two sides as injection, and one is the output side. So we have these small pipelines. They inject the water or oil or gas and see how fast it is flowing, and they find to measure the permeability using these equipments.
The objective of today's lab is to measure the absolute permeability of water using method based on Darcy's theory. And the experiment model was designed for this laboratory to measure the liquid absolute permeability. The model is comprised of pressurized Hassler cell as a core holder, a sandstone core sample, valves, and pressure gauges to measure the pressure in and out pressure, and a scuba.
These rock samples, they take from the reservoir during the drilling process. These cuttings or rock samples they take during the drilling process, and they store them in their laboratories, and they use them to find out the porosity, permeability, and so on. Because porosity, permeability is going to be used for total gas in place, total oil in place.
With a constant flow rate to measure the flow rate coming from the pump. First, the core was fully saturated with water or brine, as Peter says, the brine with 0.4 weight percent KCl. Before backing, brine water is used to saturate the sandstone core to prevent any reaction between water and clay particles inside the core. The length L and the radius R of the core were then measured using caliper. So we use the caliper to measure the length of our core sample and the radius. And as I said, the length of our core sample is 7 inches and the radius will be 1.25 inches. Then brine water was used as the injection flow rate for this experiment. As we know, the liquid data, raw liquid, or the density of our brine is 1.02 gram per centimeter per cubic centimeter, and the mu water, or the viscosity of the water, is 1.04 centipoise. Three different flow rates, 1 milliliter per minute, 2 milliliter per minute, and 3 milliliter per minute, were applied by using the ESCO pump, and the stabilized pressure is determined each time by using the pressure gauges here. From all these data, the absolute permeability is calculated using equation number 1 in your manual, which is basically Darcy equation. Q is equal to K multiplied by A multiplied by delta P divided by mu multiplied by L. Procedure of this experiment is basically, first we measure the dimension of the core sample L and the radius R using the caliper and ruler. Number 2, open the pressure acquisition software and then calibrate the pressure sensors. Number 3, make sure all aburts is tightly connected, otherwise you might have leak, and that will lead us in the inaccurate measurement. Number 4, start a pump with the lowest flow rate, which is 1 milliliter per minute, then monitor and record the pressure when it's stabilized at the pressure at the beginning and the pressure at the end of our core holder. Then whenever the pressure is stabilized, we will record P1 and P2. Then number 5, repeat step number 4 with different flow rates, which is flow rate which is to record is plot
Sir, your mic is muted.
Yes, so that was about the reservoir fluid. Let me open the presentation again. The purpose was to tell you that what kind of the experiments that we do in the lab. In the reservoir fluid lab, we try to find out what is the bubble point pressure or dew point pressure. We try to find out oil and gas formation volume factors, gas oil ratio. And after 1 week, we will do one course on reservoir engineering, and there you will see that how we can use these properties in oil and gas calculations, especially to find out the total gas in place or total oil in place, how these properties are used in one. These properties are obtained from the lab using the PVT equipment. And for the samples, we have, during the drilling process, we take the downhole samples. Okay, and usually drilling process, we do that. And when you work in the lab as a student, it's very hard to get the real sample under real conditions, because the real condition are live sample, we call it, is around 2000 psi or 100 degrees centigrade, let's say, as a general. So these are the real, and the dead oil is around 14.7 psi, a normal temperature. So we don't have the real live fluid sample. We just take the sample and make it live again during our PVT equipment and so on. So that's all about the reservoir fluid and reservoir rock. And now I will share with you the presentation that you are going to have tomorrow about it.
Sorry, I have a question.
Yes.
Except for the PVT analysis device, are we supposed to know the name of the devices that were mentioned in the video and how they operate?
I mentioned two devices mainly. One is the PVT one, other one is the core flood one. That's it. Okay, the other device you saw in the videos was the core flooding mainly and the CT scan. There was no other equipment. And for reservoir rock, you have to use the core flooding. Core is the sample, the rock sample that you take for the analysis. And core flooding means you flood the core sample with oil and check its permeability, absolute or relative or so on, whatever is your plan. And for the PVT analysis, using the PVT equipments, we find out these properties as we discussed here, these one. And all of these rock and fluid properties are used in the calculations, in reservoir engineering calculations. Let me try to open. Okay. Here is the PVT analysis for all reservoir. This is the same equipment that you just saw in the video. This one. And when you prepare for this kind of presentation, your first should be the PVT analysis is used to answer these questions, as mentioned here. Answering these questions require the phase behavior of produced hydrocarbon. Now, what is the phase behavior? Phase behavior we just discussed. It's a graph showing the behavior of oil and gas inside the reservoir at different pressure and different temperature. It's already mentioned here. What are the tests we do on this equipment? We have a test called flash liberation, a sudden pressure drop. and maybe we have another one, gas liberation, flash and differential liberation, the other one. When we do these kind of a test, we get something, a graph like this one. When we have a graph like this one, when their intersecting point is the bubble point, then what is the bubble point? Is the point where first drop of gas comes out, as we also discussed. Then we develop such kind of a phase behavior curves where we have the bubble point, and it tells us that how much liquid or gas we have, as we mentioned here in this picture. Okay, so this is the phase behavior, exactly this kind of phase behavior. And in this description here, the description for these are given actually. Then here is the situation when the fluid comes out of the reservoir through this the Christmas tree. Inside the separator, the above part is the gas, lower part is the oil. And they convert the reservoir to surface volume relation. They have some volumetric calculation to find the initial oil in place, and they are using them. So you have to put them also, and this is the flash liberation test which they do. Means they reduce the pressure suddenly and see the effect on it. Then they have the composition analysis, another test which they find out how much is C1, how much is C2, how much is C3. So this is the equipment, they call it GC. This is not the same experiment we are talking about. This one, phase behavior, is connected with this equipment, PVT equipment. Then the second one, which we find out is this equipment. It's called the GC, gas chromatograph. And its purpose is to find out exactly, for example, you have 1 liter of, let's say, Coca-Cola, Pepsi, or any soft drink. How much sugar it has, let's say, or how much water it has, or how much color it has. So different, what is the composition of that one, and how much is the exact amount each has. So in order to, for the crude oil to find out same thing, how much C1 we have, C2, C3, C4, C5, C6, as we discussed in the reservoir fluid chapter, this GC actually tells us that how much is the composition of the fluid. And if you read it, it will tell you very nicely what we are talking about. See, you can see that based on the peaks, they find out we have CO2, we have C3, we have C4, we have C5, we have C6, C7. So it tells us basically the composition of the crude oil, what exactly, based on these peaks. If you want to read about it, it will tell you here. For example, here you see C2, how much it is, C3, C4, C5, C6, C7, C8, C9, C10. As I mentioned that we don't write methane, ethane, propane, butane, hexane, heptane, octane. We write like this, C2, C3, C4. So when we say C5, we should know that we are talking about pentane here. Or when we say C6, we are talking about the hexane here. And what is the difference is the heating value. Heating value, as you go down, the heating value is increasing. And the third thing, we talked about the equation of state. What kind of equation of states we use? And we said that in order to use the mathematical knowledge, mathematical models, we have to take that physical condition of the fluid and put it in a mathematical model so that we can do our simulations. So for that, also he will talk about the equation of states somewhere. There are so many. So it's basically, it's a very simple presentation. I hope you will be able to write down in a very nice way this one. Then let me share the other one. Okay. Now, here the concept is about the relative permeability. And what is the relative permeability? We say that effective over the base, total permeability. And again, it's talking about the core flood experiment in the laboratory, the one you saw in a video. So he's talking about the same experiment. They are first flooding with water, then they are flooding with oil. And using this one, they are trying to find the relative permeability and so on in the core folder. They generate this kind of a graph. Using this experiment in the core flood experiment, they develop this kind of a graph. This graph came from the experiment you just saw in a video, this one. This is the same equipment. We are talking about the core holder. If you see that in a video, I showed you a core holder. Core holder had lots of pipes, and it has the reservoir connected to it. And first what we do, we put the core inside it. It has the inside input injection pipe at the output pipe, and we find out under high pressure, we send the oil and water, and we check its flow rate, and we develop then this kind of a graph using this in core holder one. And again, we talk about CT scanning as a video. You remember we talk about the CT scanning. and so on. So here it is talking about the wettability, second property, which is about the wettability. Wettability, as we also discussed, it's the ability of the rock to stick the fluid, how much fluid is stick with it. So water wet means water is sticking on it more. So this is what he's talking about, is relative permeability and wettability, so on. This one is actually more interesting one, this topic, than the other one. It has more information than the other one. So if you can catch this information, you are a half reservoir engineer. Then the oil wet system is talking about, you need to read about it, what it is saying. Very nice information about these graphs is given here. Then the calculations for relative permeability in the experimental. See how much you can grab out of it. So the laboratory tests. These are the tests done on the core flood equipment, the one we showed you just now in the video. I will upload that video also so you can know about the core flood and so on. And that's all. Basically, it's talking about the connection between the relative permeability and the wettability, how they both are connected, and which equipment is used to do this kind of experiment is the core flood that you saw in a video. So that's all about it, this one. Any questions? My main concern will be those who are going through this course, how much they understand this graph, this one or this one. They all are same actually, but what they are trying to say. If you can describe this graph, as I said, you are a reservoir engineer. That's it. I will term you as a reservoir engineer. If you can describe these graphs here. This is all the reservoir engineering. And we will talk about it more in the reservoir engineering course. So do you have any question?
Doctor, please.
Yes.
If we use external sources, it's normal.
Why not? But external sources for what? This is the
for this presentation.
For me, if you prepare from this material is enough. But for your more explanation, you can refer the external. For example, maybe you don't know what is effective water permeability. So you go for the external reference, you find out what is effective permeability. That is good for you, but for the presentation, don't put. Okay?
Yes.
For example, you don't know what is effective gas permeability. So what you will do, you will go on Google or somewhere, you find the information of, but this is for you. For the presentation, you use exactly what is given in this chapter as it is. For example, maybe you don't know what is this KRW. So you find out from the Google, what is KRW. So, but you don't need to, put that reference here because KRW, I'm sure somewhere you will find it about this information also. And also, for example, you don't know what is NMR scanning. Again, you have to go through the Google because you cannot find the information about here. So from Google, you can find out. In this case, yes, you can put the information because NMR is not given, not a lot of information is given about NMR here in this chapter. So you can put the information from external source here, for example. Okay. For example, you don't understand what is water wet system. Again, you go back to Google, understand and come back here. It's okay. It works, yes, I can say. Okay. Any other question? As I say, this is, take it as a challenge. As I said, if you can do this one, you are a reservoir engineer. If you can explain it very well. And then you should go for master's in it. Then I will tell you. Okay, so that's all for today. And inshallah, we'll do the presentation next week or next class about that.
Sir?
Yes.
I had a question about engineering laboratory. Can I ask you now?
Okay.
You put a folder on a Google Classroom.
Okay.
You said submit both of the lab reports here. But
Yes.
we have one lab report and we have another report which you set a separate folder for it. I want to know what is the next lab report that.
The lab report one has one is for the flow devices, flow meter, and other one was the pressure dropper, if you remember. You did two calculations there in first lab.
For the first lab?
Yeah, you did two. One is for the flow rate.
Yes.
Other one for the pressure drop.
Yes.
That's it.
So we write two separate reports for that.
Yes.
Okay. Okay. Thank you so much.
Okay. Any other question?
Doctor, I have a question about SPE. You emailed about registration for Zoom meeting,
Yes,
if I'm not wrong.
yes.
But we cannot register by this link.
Okay, I'm sending you the updated link. That one is working.
Thank you, Doctor.
Okay, I will send you now. I have the updated link. Which one is working? So I will send you that you can use.
Thank you.
Okay. Okay, then see you tomorrow again in the SPE lecture. I will be there hosting it, and see you there. I will also learn with you the software. And the details are ready. After you register, you will receive the email about the material and software and so on, all the information after you register. So I'm sending you the link again on Google Classroom. Okay, see you guys then tomorrow.
Thank you, sir.
Thank you.